So, welcome everyone. This is the one but the last lecture in this cycle. And so next week I will also do a Q&A session. I suggest, you can bring your questions just next Monday. However, experience shows that if I have the chance to prepare it a little bit, I can give you often a better answer. So, because maybe I pull out the right kind of slides. So if you share your questions as early as possible, preferably until Friday, I can better answer in the Q&A session on next Monday. Yeah? We may still do a few contents next Monday, but the emphasis should be on Q&A and bring your questions. Especially questions about the lecture. The exercises I would ask you to ask your tutors. Okay. So last time we were in the middle of looking at the optimization of gradient descent, and that comprised initialization, that comprised different kind of optimization methods, which we treated rather shallowly. And the core idea is that there are some variation typically of Newton's method, which works with the derivations and the Taylor approximation. And so that's what we used here, the Taylor expansion, and then our typical method of setting the derivative to 0 and computing the next weight from this. And of course, this also works in several dimensions. Only then the picture gets a bit more complicated as the gradient, of course, constitutes a vector. And the second derivation is the Hessian, which then constitutes a matrix. And we mentioned briefly that this may lead faster to the desired optimum than just using the gradient. The Hessian can be investigated for what kind of eigenvectors it has, and from that one can look at the curvature of the Hessian, whether it's convex or concave. That then gives us nice results. Typically it's neither, and that's the way we should compute it, is by a linear equation system, solving this linear equation. Now, when we have strongly convex functions with Lipschitz Hessian matrix, so we had convex functions, for example, for which kind of machine learning paradigm? So? The squared error loss in general first is, this describes a parabolic picture, but here, of course, we look at the influence of the weights. So we look at, how should I say this? Let me think. When we always have the squared error loss, do we always have a nice shape? Certainly not, because the combination of weights in a feed-forward network with multiple layers may distort this nice parabolic shape. And so even though the function that describes the error loss as a quadratic function no longer receives linear input, and because it no longer receives linear input, the overall shape of the function is also not necessarily convex or concave anymore, right? So yes, the squared error loss is one function which has this nice shape, but depending on what I put in, the overall function is not necessarily anymore a nice convex function. We have seen another paradigm where everything we combined led to a nice convex function. Beta has? Beta hat? Sorry, I don't understand the word. Yeah, for support vector machines, exactly. For support vector machines, we had this optimization. And there we said, okay, we have a convex function, the output of which we put into a convex function, and the result is then, or a superposition of the two convex functions is again a convex function. Exactly. So that's where we then have a nice shape and can possibly converge faster. And here comes another thing into the game, namely the Lipschitz property. What is a Lipschitz property? Well, when you look at the function evaluation in two different points, then a property which is often desirable is some Lipschitz bound. Okay, so let's assume we have some random function, and now we have two different inputs. Then there is a certain input difference here and a certain output difference between these two on the other axis. Now, for specific functions, we may be able to state a Lipschitz bound, which basically says that this increase here is less than L times the interval here. This is not possible for all functions, obviously. For example, we may have a function that goes to infinity as it approaches the origin, and then of course on this open interval from, let's say, 0 downwards, we have an arbitrary inclination, and we cannot give such a Lipschitz bound. The Lipschitz bound is interesting if it's rather small. I mean, if you have a Lipschitz bound that's 1,000,000, yeah, so where this increase can be 1,000,000 times the input interval, then we really have a strongly sort of like a small change may lead to a very different result. And typically what we're interested in are Lipschitz bound such that a small change only leads to a small change in output. And when we have such a kind of system, this is, for example, beneficial for the learning of dynamical systems. Yeah, when you steer the car, that you have the property when you steer the car a little bit, that the output is a little bit different and not exponentially different. Because if it's exponentially different, that would mean then that you really sway the car so much that it may topple over and you have an accident. And this Lipschitz property, which we look for such dynamic systems, also, well, it's a very general concept, is used here. If we have a strongly convex function with such a Lipschitz-Hessian matrix, which then basically says that the difference, the Hessian difference is less in these 2 points, is less than the difference between these 2 points times this Lipschitz constant, then we have a quadratic convergence. But as also said here, this convexity is not generally given for neural networks. Here, SVM is mentioned here actually. So this convergence is typically not guaranteed for our neural networks. And we can imagine that we might get stuck because of the many non-linearities and the many different valleys and hills we may have in our complex function on a very large input space. What is a little bit surprising is that one rarely gets stuck with very high dimensional inputs. And the reason seems to be that we have so many dimensions that you always find a way down. So when we have such a one-dimensional function, let's take this one, and you are here, even if there is yet a better value here, from here this is very hard to find. Because it's very hard to get out of this valley. I'm not sure I can dare to draw this in 3 dimensions. In 3 dimensions, you have already valleys that do not just allow me to move in this direction, or these directions, but I can move in these directions, but also forward and backward. So in a 3-dimensional landscape, I have a much better chance of finding a way out of such a valley than in a 1-dimensional landscape, because I have 1 dimension more. Still, in such a 3-dimensional landscape, the chance of getting stuck is still very high. But we don't have, in neural networks, 1 or 2-dimensional landscapes, but we have landscapes of tens of thousands parameters, or millions of parameters, or even more. So the chance of getting out of such a local optimum are very good. And once we're out in one direction, we can maybe go in another dimension, move in another dimension to get further out. So practically speaking, we usually get out, or we're usually not that easily stuck in local optima as one might expect when one looks at the 1 or 2-dimensional counterparts. Still, there will be many local minima. The question then sometimes is, maybe these different minima are equally good or almost equally good. And this can even be a beneficial factor. Okay, now how do we compute, or how do we optimize our weights when we have small data set sizes? Just a few thousand data points. We compute the loss and the gradient. Here we have the gradient of that loss, varying the parameters beta. And with these parameters beta, the function f is defined on the input, and we compare the prediction to the labeled output. And then we just use our gradient-based methods and use all the data from I equals 1 to n at the same time. That's called batch learning. We use the whole batch of data at the same time. For very large data set sizes, where we may have millions or billions of documents, this is not a very efficient procedure. And rather what you do then is that you define subsets of the data, so-called mini-batches. And you don't compute this loss globally for a particular parameter configuration, but you compute it just for a much smaller batch size of maybe 100 or 1,000 data examples. And this leads us then to stochastic gradient descent. So you take your very large data set and you sample data items. That brings you to a smaller batch size. This is, of course, a stochastic process. You sample stochastically. And then you compute your loss and the direction in which you should move in order to minimize the loss based on this much smaller data set, d hat, which is a subset of d. And then based on that, you do your gradient descent. You take your current parameters, are the previous parameters minus some step according to the gradient. And so this of course also means that you are blind to some data, which is another effect why it's easier for you to get out of local optima. Because even if you're stuck right now in a local optimum, this being stuck in a local optimum is according to the current mini-batch. With the next mini-batch and the next data set, you have basically a different loss function, because this loss function is determined by this d hat. So by switching between different mini-batches, you effectively switch between different evaluations of loss functions. And even if you're stuck with one particular mini-batch in a local optimum, the next mini-batch may help you out. The question, of course, is how do you define this eta, the learning rate? And one possibility is that you do exponential cooling. So you start with a certain parameter. I mean, of course, eta 0 must be below 1. And then each time step t takes the exponent of that base, which is smaller than 1. And as you move forward in time, as you move forward in the learning steps, the learning rate gets smaller and smaller and smaller, approaching 0. With Newton's method, what you try to do is you try to directly find the intersection with where the value is 0, right? And when you apply this, of course, to the first derivative, then you approach the optimum. This is one possibility. The other possibility, which currently is much more used, is that you use stochastic gradient descent with momentum. Maybe first, what is the problem if you try to apply Newton's method, and if you just apply gradient descent? Then in your landscape, you can have, for example, such kind of saddles with almost 0 inclination. And that, of course, means that the gradient does not clearly show you where to move. Yeah, when you're at this point, should you move in this direction or in the opposite direction? This is not quite clear. And even if you have a signal, the signal is very weak. So the idea is that if you start in one point, you basically do as if you have a ball that rolls down the hill. And if when the ball rolls down the hill, at this point it has a certain momentum, a certain velocity. Well, momentum is nothing than velocity times mass. Yeah? So you have a certain momentum, and you keep the ball, you keep up the speed of the ball. And so with this given speed, the ball is carried over this flat space. It's even carried over a small minor hill. And this is what is done. This is what is done here, but doesn't show. Here. This is what is done here. So you compute the change of your parameters by saying that you take the previous change and subtract from this previous change the change that you get by looking at the gradient. And then the actual change of parameters is done by looking at the previous configuration of parameters and adding this delta beta. So this delta beta, when you look at this line, this is the stuff that you had before, right? But you keep the previous change of your gradient and remember it. And this is a bit like you let the ball roll down, and as you catch up speed, you remember that speed and only gradually decrease that speed again when you move uphill. There are variations of stochastic gradient descent with momentum. One is the Nesterov accelerated gradient. And I think that's easiest to understand with such a diagram. So the default method that I showed you now with momentum is that you are at a certain point and the gradient shows in a particular direction. And you also look at the speed. And the speed points to another direction. And so the new parameter configuration is the old parameter configuration plus gradient or minus gradient plus this momentum. The little bit awkward thing is that you're guaranteed to be transported from here to there. but you measure the gradient not at this point, but you measure the gradient at this point. And so the idea of Nesterov accelerated gradient takes this idea and says, I'm here and I have some velocity, some momentum. I'm guaranteed to move here first. At this point, I compute my gradient, and this gradient will point me in the right direction. And when you compare the two pictures, so maybe this one here puts you a little bit too far right in comparison to this one here. So yeah, you do a correction, you do one computation less, you could say, yeah, because you first do one step and then already correct according to the gradient in this area. And this is just a minor alteration of defining this delta beta, because this is the same formula as above. And you have the same previous, the same memory of your previous velocity. The alpha may moderate this previous memory and say, I don't want to memorize too much. I want to weaken this memory a bit. And but you don't evaluate your gradient at the current position beta, but at the position beta plus delta beta according to the delta beta that you had at this point. Okay, so now what are the trade-offs? The higher order methods that use the Hessian promise faster convergence. But the problems are that many of our optimizations are noisy. Because we have these mini batches, because we have regularization. Actually, you haven't seen the regularization fully yet for neural networks, but that's something we need to do for the same reasons that we needed regularization in all the other paradigms. And so the dominating methods these days for optimizing neural networks are first other methods with momentum, or more recent developments, stochastic Newton methods, which I don't explain here. Okay, but you have an idea that maybe for different kind of contexts, you may want to use different kind of optimization methods. The most used method, and as I said here, I mentioned this in passing, it's not part of the exam because it goes into very small, tiny technical details that I don't think are so important for you to memorize. I mean, obviously, when you use a certain method, a default one to use is Adam or its improved version NADAM, and you should understand how it works, but I don't want you to memorize that. I mean, if you do, it's fine, but I don't expect it. One crucial step in what I've described to you is the question how to set the learning rate, eta. If it's very small, then you have very slow convergence. You have to do a lot of computations to do very small baby steps forward. If you make eta too large, then you may jump over optimal values, and you may also have a problem with convergence. So this may be very unstable. And Adam tries to adapt this learning step size. And so this is the algorithm as given in the neural network book. And what does it do? Well, it requires initially a step size and some exponential decay rates for the moments. Here you have your objective function with your parameters that you want to optimize, and initially you start with a parameterization of theta 0. And then you have a first momentum and a second momentum and a time step counter. And as long as your parameter optimization is not converged, well, you go to the next time step. You get the gradients of the previous iteration, and then you have a first momentum, and well, the first momentum is like the velocity or the momentum of your speed, and you have a kind of second momentum. And both of them are updated with some update rates beta 1 and beta 2. And the update of this first momentum happens according to the gradient and some memory of the previous value. And the update of the second momentum happens in the same way, but the gradient squared of the gradient. And with this, you then sort of normalize, you compute a bias-corrected first moment for both, and then you actually do your parameters update, and basically this is the simple, you have the learning rate, and you subtract this part, which aside from normalization was just a version of the gradient, and the memory of the previous velocity. But you divide this by the second momentum, which was defined here. And this second momentum, I mean, if you remember the formula with Newton's method, is a bit like this is the first derivation, this is the second derivation. So you try with very simple methods to replay this update that we saw with the Newton steps. This is, of course, a very coarse approximation of the Hessian. But it's easy to compute, and one achieves in general better results than with the simpler methods. NADAM is a minor variation of that. It then just applies the Nesterov accelerated gradient principle to this computation. So it looks where will the momentum carry me and compute the gradient at that point. Computing a gradient is always compute intensive, while just forwarding the momentum is a very simple operation. And there is tons of literature, of course, right? So one could do a whole lecture series just for optimizing gradients. This is a nice figure from a student. I think it was his master thesis, Yusuf Tuti. And I really like this figure. So he compared in a specific setup the progress towards the objective values with optimizers. And he had different optimizers here. So this slow one, I mean, this is the objective function. How does it go down? This was stochastic gradient descent, so the vanilla version. Green is RMS prop, some well-known old method for optimization, some version of Newton's method. Then the red one is Adam, and the blue one I think was Nesterov Adam. And you see how much quicker this Adam performs compared to the established methods and the vanilla version. So this is really orders of magnitude faster convergence with these improved methods. And that's, of course, the reason why you should use it. I mean, there's no guarantee that it will always be the case. As often in machine learning, the context may decide, but it's definitely one dimension to consider when you want to learn your function. There is also some nice webpage. I didn't check it out this year whether it still exists. I hope it does, where you can play around with different configurations. You have a function and you start in one place, and depending on how you define the momentum, what part of momentum you have, you can sort of you will end up in this local optimum, and of course what you want to do is you want to find this global optimum. Okay, questions so far? No? okay, I mentioned already that for the same reasons that we have in other paradigms, we also want to do a regularization for deep neural networks. And so I used the term regularization before. I wanted to restate different definitions for regularization. And I didn't mention all of them. They are not identical and focus on different aspects of the term regularization, though they all look towards the same eventual objective. So in the neural network book, Goodfellow et al., they say that regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. So, I mean, you can always bring down or almost always, not completely, almost bring down the training error down to zero. Of course, we have Bayesian error that we cannot get away with. Wikipedia says, and I also like this definition, regularization is the process of adding information in order to solve an ill-posed problem or to prevent overfitting. Do you know the term ill-posed problem? Yeah? It basically means that there is not a clear solution for this problem. And even if there was, you may have a hard time to find it. But for a loss function, obviously, you may have several minima that share the same value, for example. And in that sense, it's not a cleanly developed problem. And it may be, well, also in addition to being ill-posed, it's maybe hard to find. And to prevent overfitting, overfitting is, of course, exactly what is described above. So dealing with the ill-formedness, ill-posedness of the problem is another thing. And yeah, we may talk about billions of parameters in deep neural networks. Overfitting, therefore, is a huge issue. And regularization is most important. So how do we describe this usually? Well, we have an unregularized loss function depending on the parameterization theta. And we have training data x with labels y. This is our loss function j, and we add some regularization term on the weights and the bias vectors, typically not on the bias vectors. And this is similar to linear regression, where we don't want to regularize the bias, the offset from zero. Because if we have a function that's far away from the origin, we don't want to force it to be close to the origin. We just want not to overemphasize the meaning of individual data points. And so we add with some regularization parameter, here it's called alpha, this loss function with the regularizer, and then end up with a regularized loss function. So that's the same basically as what we did for linear regression. Now, we can do rich regression, L2 parameter regularization. So there, what we do is we add, for the weights that define our connections between different neurons, the size. And the size squared is nothing else than if we have a weight vector, the weight vector transposed times the weight vector, so that's the dot product of the weight vector, where the weight vector really comprises all the weights from across the whole network. And as I said, typically not the bias vectors. And then we have some parameterization, which we can call alpha half. And if we then compute the derivative with regard to W, the derivative of this is just alpha times W. So that means the regularized gradient is the old gradient plus some memory, but some reduced memory from the old weight vectors. And when we then update W with that kind of additional memory of the old weight vector, it means that we take the old vector minus epsilon, and here you see we subtract a little bit from what we had before. and we subtract a little bit from the gradient. So this means in every step that we optimize, we try to make our current parameterization vector a little bit smaller. We try to push it towards 0. Of course, we can also do the same thing. Instead of doing the square of the weights, we could also take the absolute values of the weights, basically some lasso, and then compute the gradient. So for the squared weights, we end up and subtract lambda w. When we have the absolute value, all that remains is the sine of w. Yeah, because the function, you remember, absolute value function is like that, and the gradient of the absolute value function is either +1 in this part and -1 in this part. So +1 or -1 is simply whether the weight in this part is positive or negative. So we look just at the sign, whether it's positive or negative. If it's positive, this is 1, and if it's negative, if it's -1. So we always subtract or add in the negative part the lambda to our gradient. And we have the same effect that we had already with linear regression, that the L1 makes the weights become sparser, because if the weight is reduced and then we only subtract a small part of the weight, then it's hard to reach absolute 0. That's more easily possible with lasso, just the same as with linear regression. We can also look at column-wise regularization. So when we look at ridge, we take the whole matrix, and I call this a weight vector, but of course, actually speaking, we often think these are matrices, but we can turn this into a vector. And what we optimize is the Frobenius norm. The Frobenius norm goes over all columns and rows and computes the square. So such a weight matrix has this Frobenius norm. But what we could also do instead, to constrain the size of the columns such that there is no unit that is very much preferred. I mean, with this approach, we could, for example, put all the signal on one unit, one hidden neuron. Well, because we could set all other weights to 0 in order to minimize this sum. But maybe that's not something we want to do. Maybe we want to say we don't want to have units that approach 0. All units should have some signal that they carry. And that's what we can do is by setting columns to regularize the columns, such that in the columns some values are different from 0. And we can do this with constraint-based learning and use Lagrange multipliers, a bit similar as we did for SVM. The message from this slide is simply, you can think of a whole range of ways of how to regularize your weights, and actually even regularize how much signal you have at the different neurons. Other than such kind of arithmetic regularization, what else can we do? And one important thing is data augmentation. This is a quote. I should have put this in a different place. I still like the quote, but somehow this year it's in the wrong place. This is Philip Singer. He is typically among the first 3 worldwide to win cackle competitions. So there's a kind of a leaderboard who has won the most cackle competitions. And you have, I don't know, hundreds of thousands of people who have participated in one or several or many challenges. And it's a bit like a permanent tennis tournament. Philip tends out to be typically in one of the top places and has been number one for a long time. Yeah, I'm not sure whether he's now. I didn't check that now. And he also gave his nice talk about how to win Kaggle competitions. And the point about these competitions is, of course, you really want for a particular task to optimize the outcome of your prediction. And this is, of course, not just theory. You need to emphasize the right kind of activities for doing so. And sometimes this includes, for practical reasons, many things that we don't dwell on so long, because I really rather want you to understand what are the concepts. But even if a concept may be rather easy to explain, maybe you need to spend a long time working on this concept when you actually try to achieve very good results, such as you need for winning a Kaggle competition. And one thing he looks at is tuning hyperparameters, which includes the learning rate and having a good setup of data validation. So it is really important that you really judge your hyperparameters appropriately, that you, when training, you really have the right kind of learning rate, and doing these things that we don't dwell on for so long correctly and spending enough effort on these is important to get the maximum performance out. And by the way, there are also nice stories from papers, for example, in the domain in which we work, knowledge graphs and knowledge graph embeddings, where you try to learn from knowledge structures to do predictions. There was a very nice paper by Rainer Gemuller and team from Mannheim, and in, I think it was 2019 or so, there was a huge number of algorithms for how to do predictions with knowledge graphs. And what they did basically was to look at the last 10 years of algorithms and do exactly this thing. And it turned out that one of the oldest algorithms around was still the most successful if you did the tuning of hyperparameters correctly. All the papers that came later, they compared against the default hyperparameter setup and then won that competition against the old algorithm. But really, just tuning hyperparameters correctly showed that the old algorithm was more or less better than all the newer ones. And so that's important to know. You don't always need the most sophisticated algorithm. Make sure you tune your baselines appropriately. And then, of course, you can look into more difficult methods and develop results for these more difficult methods. So, topic in this unit, however, is regularization through data augmentation. This can be quite simple. For example, here we have this nice picture of cat, and here we have another data item. What has changed? Look here. I have inserted a few black pixels on the left and cut the photo a little bit on the right. But of course, when you say this is an object X, the label of which is cat, then this also is object X, the label of which is cat. There should not be a problem with the fact that now the pixels have been moved a few pixels. Yeah. So what you get a new object, the same label, and you don't have to do very much for it. You just shift it. Of course, you could also do other things. You could also stretch the picture. Zoom in. You have to be careful, of course, that the object that your picture is labeled with is still visible, right? And you could also just flip it. I mean, even the cats, they look very much different, right? So, of course, it's the same cats. It's just like, just flip the picture around. And again, that's new training data for the same task, and you can even be sure it is still a picture of two cats. You have to be careful sometimes But first here, I mean, people did this, for example, for digit recognition, so handwritten digit recognition. And what you can also do to make the whole recognition more stable is to inject some noise. So if this, for example, is an input image, which is labeled with 6, yeah, this is the same picture, but here you put some noise filter over it in order to and of course, you can, as human, you can still recognize this or this, which is the same picture but with some added noise. You can also rotate it, right? So this is a rotation. This of course, a bit harder. I think here I have real difficulties in understanding that it's a 6. And of course, you have to be careful because at some point the 6 becomes a 9. So you could, of course, if you're not careful, introduce some learning problems. Another problem when you do provide training data, you have to be aware that most data sets have mistakes. So either mistakes by omission, that there is something on a picture that is not labeled, right? Just because the human labeler got tired and forgot to label it, or really oversaw it or whatever, or even a mistake. You have some interface, you pick a label and you hit the wrong button for labeling. And then of course this means that you have some mistaken data item. So what people try to do, of course, is to let objects be labeled not by just by one person, but typically by 2 or 3 people. So you have, and the more difficult the labeling task is, the more you have to invest into redundant labeling. I mean, labeling this with cat is still rather easy. I mean, labeling this with 6 is already pretty hard, and you may have very different annotations from your crowd labelers. So when you have mistakes in your labels, y, and you try to maximize the logarithm of p of y of x when y is a mistake, this may be very misleading to your training process. Because you first try to learn what is a cat, and then you have a dog there and call this a cat, yeah? So you push the prediction engine away from the correct result. And you don't allow with the default training regime some mistake. And Softmax tries to learn 0 or 1 for a category. You have one hot encoding, right? So all the labels are 0, only one, the one that is given, you say it's a 1. And then this label of 1 may be even impossible to reach when you have mistakes in your training data set. So, well, noise may lead to wrong values, or and one partial solution that you should consider is to model the noise in your labels. So when someone says it's a cat, don't say there is a 1 here and a 0 in the other places, but keep some noise epsilon and distribute this noise over all the other labels to basically express that with a very high probability of 1 minus epsilon, it's a cat, but with some other probabilities that are different from 0, it could be a dog or a car or something else. So you don't push the training regime as hard to achieve an unachievable objective. And it's very easy to implement. This, of course, is just one regularization, not to overfit too much to a data set. These different strategies are like doing, for example, rich regression, data augmentation, here this modeling of label mistakes. These are not substitutes for each other. Rather, you may want to use all of them. You want to really combine them. And this one in particular, of course, is super easy to implement, and you can combine it. Another regularization possibility is to inject some noise into the weights. So you wiggle the weights with some noise and then compute the corresponding loss and the gradient. And well, we could put this also in the regularization term. Again, one of the effects is that when you just wiggle a bit and you're stuck in a local optimum, because of the wiggling, you can get out of this local optimum. Another one which is super helpful is multitask learning. So a typical process is the following. You have your object description, your X, then you have your feed-forward network. And the feed-forward network may have one hidden layer or even 10 hidden layers. So let this layer stand for an arbitrary number of hidden layers. And then you have one label that you want to achieve. For example, you want to express that this X is a cat. So that would be one labeling process. And so you have here one or several hidden layers. And here you want to say it's a cat. Then, if you just consider this path, well, here is one layer before the final decision. What is the ideal? Of course, in general, you may think of other tasks. If you want to classify for cat here, you may want to classify for it's a landscape picture or it's an indoors picture. And the next task could be it is a photograph or it is a painted picture. So you can have very many different decisions that are orthogonal to each other. One idea is that when you have several tasks such as cat versus dog, indoor versus outdoor, photo versus painting, etc., they all work on the same input. And you want to characterize these outputs by similar considerations. So what if these similar considerations are captured in this one or several hidden layers here, in these shared hidden layers? So you have one layer which is tasks, which you learn, which is task specific, cat versus dog, or indoors versus outdoors, or something else. But before that, all the large network, you use exactly the same network. And you train now your objects with different labels along overlapping pipelines. Yeah? So cat versus dog, you train in this pipeline. Indoors versus outdoors, you train in this pipeline. And so in this part, you learn shared weights. And these shared weights help both 2 or 3 pipelines. And the idea is that when you learn what kind of objects you have, cat, dog, indoor, outdoor, the one task helps the other. Because they're overlapping features that you learn. And so this is a common, and this is also why it's sometimes called representational learning, or often called representational learning, that you use neural networks for representational learning. You learn a representation of your object. And this learning of a representation of your object happens here. It's typically not one hidden layer. With one hidden layer, you don't learn a lot. It's typically more like 10 or 20 hidden layers, in which you learn a representation of the object, and then you have 1 or 2 layers that you use on this representation to make your final classification. And compared to the old methods, doing representational learning was the biggest achievement for machine learning. That you no longer say this is the way an image should be interpreted, but you learn this representation. Another regularization method, again combinable with others, is early stopping. So you do training and you have a training set loss. And as always, training set loss goes down, down, down. It still goes down, though maybe very, very little. But how does the validation set loss perform? At some point, you run into overfitting. And so validation set loss goes down, but at some point it doesn't improve anymore and may even get worse. So what you want to do is you want to determine an optimal point. So the optimal point is here where you hit this horizontal bar, and that's the point that you want to take to fix your classifier. And this is early stopping. Of course, for early stopping, it's maybe not even the best name. For early stopping, you basically, of course, you have to go longer to find what was the best point. But you don't take the result from here, but you take the result from here. So here, training loss was not that great yet. And well, again, you can also apply this to backing or boosting. There's also the question, how many simple predictors do you combine when you do backing or boosting? Yeah? You have, with the same rationale, you can do early stopping there. Just last year or so, I found this paper, which is not peer-reviewed yet. It's only available on arXiv, so by some very experienced researchers. There is sometimes unexpected behavior. And so here you see what is the accuracy. So higher is better. And what is the accuracy of the training data? So initially you have very low accuracy of the training data, then it goes very high. And then you are perfect with your training data. And you might want to stop here. However, they observed that by continuing training on that data, continuing data, the validation data may suddenly do a jump. And I mean, here, this is a logarithmic scale. So here you are in the order of 200, 300 examples where the training accuracy goes up, but then it just still takes a very, very long time until the validation accuracy goes up to a very good result. I mean, early stopping might tell you stop here, yeah? But that would be a super bad result, accuracy of maybe something like 3%, whereas here you have accuracy of almost 100%, 99% or something like that. They called this grokking. I also had to look up this word. It means something like understanding. It's a bit like it's confronted as long with data and learn, and you're only released when you have finally understood what the classification problem is about. But I have to say, I cannot quite put all this in a completely coherent picture. I mean, this is now from 22. I said not even peer-reviewed, and there are still many effects with understanding the learning behavior with regard to training and validation. And many people still investigate this. I mentioned this before. I should maybe have placed this in the previous unit. Instead of regularizing the weights, you can also regularize the hidden units. So here you have a y, and here you have the input. And well, you take the input times the matrix. And in this matrix, this is regularized, so you have many zero positions. You could also try that the hidden layers you use have many zero positions. And the matrix is maybe a full matrix. And then you compute the result. So here you have a sparse weight matrix, many zeros here. And here you have a sparse representation, many zeros here. So that's, by the way, another possibility. I don't think I've seen this that much, I have to say. Another important and currently much used regularization technique are adversarial examples. Who has seen this picture before? Because it's a very popular picture. Okay, and who has not seen it? Just to make the counter test, okay, about half-half. So what does it describe? This is a picture of a panda, and you train your network, and it says correctly it's panda, and my confidence, my softmax gives me 57.7% confidence. And now you change this input, and when you change this input with some noise, and you take this picture and you add 0.007 times this noise, you end up in this picture. So for you and me, this is basically the same picture. But it's a different vector and different input vector. Only we cannot really see the difference. But when you now give this picture to your prediction, then it returns Gibbon as a result. And even with a very high confidence. And so this disturbing noise here is basically an attack on the classification mechanism. I mean, here it's harmless because instead of a panda, you say, okay, I have a gibbon. There are other examples of pictures where you take a stop sign and you put some black dots on the spot sign and it says maximum speed limit 50. So instead of stopping, you would be propelled to go 50. That's, of course, a major difference. And just these days, I have seen another adversarial attack that changes a single picture in such images, and it looks for which single pixel is to be changed, and also changes the classification with that. So this is an easier method because you basically look for how can I modify my classification outcome, in which direction, in order to come to a different classification result, and you look for the closest path to this different target, and you look for how you can approach this, and then you construct this kind of noise pattern on top, which we cannot recognize. Now, what you can do, of course, is, as adversarial training, you take such specific attacks, and assuming that this is a very small change of this picture, you say such an attack picture must also belong to the original category of panda. And maybe you can even visualize this a little bit. So let's assume you have here an input space, and here you have pictures of pandas described with P, and here you have described gibbons. Then, of course, what you learn is a dividing line. A line, I mean, maybe straight, maybe it's curved, doesn't matter really. Let's curve it a bit so you understand that we don't have a linear classifier. And now you have a test picture, and this test picture is this P tilde. And this P tilde is in the range of the examples of panda, but with a little bit of noise, you just push it over the boundary. And then it's mistakenly classified as gibbon. So if a little bit of noise to such a test picture can push it over the boundary, what do you want to do is you want to say, this is the wrong boundary. Let's push the boundary such that a little bit of change does not push me over this limit. So this is an adversarial training. Okay, then yet another regularization method. So you see there's tons of regularization methods here that you can again combine. Again, so this adversarial examples, adversarial training is something you can combine with the other regularization methods. A very much used method with deep neural networks is dropout. What is the intuition? In every learning cycle, you eliminate some units with a certain probability. So if this is a certain layer, you just cut out units and don't propagate information in such a learning cycle. What is the rationale of that? The neural networks may have a tendency to exactly remember particular pictures. And this exact remembering is disfavored if such an information channel is not reliable. Now here this is dropped, next round this is dropped, and the one after this is dropped. So there is not a specific pattern that you can memorize 100%, because whatever pattern you recognize exactly, some part of that pattern information will be disturbed by dropout. So the intuition is that you don't want to rely on a single feature, you rather want to spread the weight assignments. You don't want to limit the reliance of one particular unit, one particular neuron, and you don't want to have overfitting one path per training example. I mean, that's what you could do. You could try to remember exactly one picture. And I think I should have a slide on exactly that. And so dropping a predecessor shrinks its influence. Yeah? You don't drop it permanently. You drop it only for some training periods, and then you reinstate it and continue training and dropping others. So if this is your feed-forward network, after applying dropout, you have eliminated these units, and you have to do your predictions without them. I mean, this is maybe a bit too much. I mean, this is like a dropout rate of half. That's probably a bit too much. And yeah, I mean, here is just some different dropout rates. I mean, you don't want maybe to drop out that much information from the input. Then here you have a higher dropout rate, but eventually, of course, you shouldn't drop this one then, because if you do that, you don't have an output. Yeah. Yeah. Yeah, that's the easiest method, that you select for each, for example, for a mini batch training, you select randomly in this layer with a certain probability the units that you drop. And everything else stays the same. So what happens now? Let's assume this was very important to classify correctly, and now this is dropped. What happens? So the loss increases. And what happens then? Hmm? Exactly. Yeah, exactly. That's what happens, right? So maybe there was an over-reliance on that node. Now it's dropped. The loss increases a lot. And as you said, the optimization of the remaining parameters will push the network to recognize or to do the right classification with all the other units. And now, of course, with all the other units, maybe the next round this one will be dropped, and then the same thing happens again. And so over time, the network is pushed that no matter which exact unit you drop, there is enough information left to hopefully do the correct classification. And so you try to avoid to being stuck in exactly one configuration. You don't want to remember one exact picture. You rather want to have the parameters such that you can nicely split up the space that you have to distinguish, let's say, different animals. There's one theory I briefly present here. I mean, but there are many theories. and it's not that one is wrong and one is right and the others are wrong. There are different ways to understand it. One way is to understand it as an L2 regularization. I mean, because you drop out things, you have to put weights on the others, obviously. Or you could say during the dropout, the weights of them are zero. Yeah? When you vary the weights by this way, by dropping out things, what you do is you also vary the flow. And this is a bit like a probabilistic process. We will talk, well, not this fall, but then again next year in fall, I talk about Bayesian networks in more depth and learning with Bayesian networks. And so you get a kind of a probabilistic approximation of what's happening underneath because you probabilistically drop out certain paths. There is one theory which says it's a kind of model averaging process because every network to which dropout was applied is a different network. And so what you do with dropout, you have many different networks combined in one. So here, dropout is ensemble training. Let's assume we have this very tiny network, and now you apply dropout. And when you apply dropout, you end up with these possibilities. Not all of them are valid networks. I mean, here you do a prediction, but you don't have an input. Here you have an input, but there's no connection to the output. So obviously not all of them are reasonable networks, but you can focus on the ones that are reasonable. And when you want to describe these networks, how can you do that? One way to do it is to add a mask vector. So you have all your original units, x1, x2, and h1, h2. And in order to model this dropout, you introduce variables that are either 0 or 1. And if they are 0, they drop out such an intermediate entity. So basically, x1 is always there, but if mu of x1 is 0, then x1 hat is 0 and doesn't exist, so to say. I mean, it still exists, but it doesn't forward any information. And if this is 1, then this value is just forwarded to x1 hat, and then this information is there. And this is not only done for this part, of course, it's also done for h1 and h1 hat, where h1 hat can be 0 if this masking occurs. And so this is a way of modifying your original network in order to still represent a single network in a way, and you add these masking vectors in order to always use the same basic infrastructure, but to adapt the learning in your network by picking different masks. Okay, now dropout training now is you want to you have here the loss. The loss depends on your parameters theta and on the mask vector. And if this is the loss, then you are interested that this loss is small for the different occurrences of masking vectors. So the expected value of the loss is if you sample from all possible masking vectors, what is then the expected loss? Well, it's a kind of an averaging over the different masking vectors. And every masking vector is a different network. So it's an ensemble of networks. So you want that your thetas are such that when you sample from the masking space, the expected loss is small. And that's why you minimize it and you look for that argument theta that produces a minimized expected loss given the different masking vectors. There are, how many masking vectors do we have? Exponentially many in the number of units, because every position can be 0 or 1. If you have 1,000 1,000 units, then you have 2 to the power 1,000 many possibilities, so many masking vectors. So forward propagation, I mean, you cannot really solve this completely. All that you can do is you can sample. So you sample from this space of masking vectors in order to compute this term. So maybe you sample and say I use 100 masking vectors, but there are 2 to 1,000 to the power 1,000 many masking vectors in the real world. Alternatively, one theory says let's approximate the whole thing. So you approximate what you learn the conditional probability by evaluating of the extended model and by using the mean value over all vector masks. Now this is a small trick. Usually one uses the arithmetic mean, and this is just so the mathematics work out. So when we look at a single logistic unit, a sigmoid, then the sigmoid is determined, we can write it in this way. And S is just the weighted summed input. And Ij is the jth input, jth output from the previous layer. So this is for a single unit. The arithmetic mean is just summing with the probabilities over the different values. And the geometric mean is just taking the outputs from the previous layer to the power of this p, depending on how often it occurs. And so the geometric mean is then just computed by this formula, and then one can also do some normalization, and what one then gets is that the normalized weighted geometric mean of these previous outputs is the sigmoid of the expected value of this input. And then forward propagation is very simple. You put into the sigmoid this weighted terms from the previous layer. The P indicates whether that particular unit is kept or dropped. So this P is just 1 minus the dropout probability. And when one then looks at the output of a unit in a certain layer, this is this output of a unit I in a certain layer H, then the expected value is the sigmoid of this weighted result from the previous layer. And so what this basically leads to is that you just reduce the result and have a way to arithmetically approximate the result of computing dropout. I have to say, this is one way to understand it. Most often dropout is really just done by applying, by deciding to turn certain values 0. Dropout is most favored, not always useful. One finds also then papers that describe where it wasn't useful. You can also try to use it for other machine learning methods. When you use logistic regression, you don't have multiple layers. But what you have for logistic regression are different input channels, different attributes. It may make sense to not emphasize one particular input channel too much. Again, you might run into memorizing rather than learning. And so you could use dropout to mute certain attributes that you provide as inputs. You could also, when you do bagging or boosting, mute certain trees sometimes, so you don't rely too much on specific trees. And here you have dropout with gradient boosting. Okay, so this was a huge part over regularization, because it is just a very important consideration when you do training of neural networks. Now, I've showed you a lot of images, and I didn't really tell you how to actually train on images. So far, what I showed you were always fully connected, or not always. We had this one example with a mixed Gaussian. But most of the time with neural networks, we looked at fully connected networks. So where you have the different layers, and one previous layer informs every unit in the next layer. Now this is a bit weird when you think about it, because the units for images, or the input units, are organized like the pixel, yeah? So if these are pixels, every pixel would be given as an input to a corresponding input unit. Now, okay, so the image can be very large, have many pixels, but now a certain figure, a panda or a person, may be in one part of the picture, but you don't really care whether the person is here or there. Now, when we take the naive interpretation of the input signal, it is a difference whether the head is described by these pixels there, or the head is described by these pixels there. There would be different input units, different weights to the next layer, different processing. So actually, having a fully connected network for an image where you want to have this translation in equivariance, yeah, when you move a picture like I did with the data augmentation, you still want to classify something as a cat. And for exactly this purpose, people came up with convolutional neural networks. Actually, it's an old idea. I'm not sure whether it's from the 80s or 90s, so, but really an old idea. So what is a convolutional neural network? Let's first look at convolutions. So let's assume this is our input. So this is our image. And at every pixel, we have a certain value. Let's assume it's a black-white image, black-gray image. Yeah? Then this would be maybe intensities. So maybe this would be 9 would be rather bright, and 0 would be completely black. So we have, of course, we would have more values than just 0 to 9. But for the sake of the example, this is a very small image, and every pixel has just one value. Now, what people initially did was to define convolutional filters, and later on they learned these convolutional filters. What is a convolutional filter? This is here a convolutional filter. It's nothing else than a certain arrangement of weights. Here we have 9 weights. And the idea of this filter is that we move this filter over our input feature map, over our image. And so this shows here the first instantiation of applying this filter to this image. And what does it mean to apply this filter to this image? It means you take a particular weight, like this one, and multiply it in this position. The position had a 3, so it's 3 times 1. You take this filter entry and multiply it with the corresponding position. This is 5 times 0, and so on and so forth. So this gives you now values, 9 values, and you add all these 9 values, and you add them up, and you end up, when you look through this, with the value 25. So by putting this value here on this image upper left part, you have now computed a value. Now, when is this value high? This value is high when you have values primarily in the diagonal. The other values here don't really help. So this filter selects in this part of the image certain patterns and doesn't care about others. This, of course, is just one convolutional filter. You can take other convolutional filters where the ones are arranged in different shapes. Maybe the ones would be arranged as a circle, or the ones would be arranged in the other diagonal. So with such a filter, you make out certain collocation of values in the original input image. And now you move this filter to the next position. And when you move it to the next position, so this would be these 9 values, you compute the next value. Of course, what happens with the filter that size and an image input feature map this size, you have in the horizontal 3 possibilities to move it, and in the vertical also 3. So you end up with an output of 3 by 3, where the input was 5 by 5. So this applying this convolutional filter to all possible places slightly decreases the size of the input feature map. Yes, exactly. Yeah. So this is just like now the one detail. Let me maybe show you an example to make this quickly more interpretable. You're not focused necessarily on just 1 and 0. You can also have -1 and 1. So this is a convolutional filter with a larger matrix and just 2 entries different. And you take the Taj Mahal, and what do you get is a representation like that. You still see, what exactly do you see with this filter? What have you extracted? Not fully. Drastic change of the color, yes, but in a certain way. So now you have to combine these two and add another aspect. Vertical lines, yeah. Because of this filter, yes, completely right, drastical change of color. And when do drastical changes of color happen? At edges, right? The way this is arranged, you don't discover the horizontal edges like this one here. That's not in this picture. What you discover are the vertical lines. So you see how such a very simple filter extracts meaningful features, meaningful vertical lines. Now, filter can be more complicated than that, but this is, I think, a nice toy example. Yeah. I would say keep this question, and when we have completed convolutional neural network, check whether you still have the question. Okay? Because right now it's just like looking at a very tiny baby step in the convolutional neural network, and the picture needs to be completed, but we are out of time, and therefore this will happen only next week. And then we will complete this slide deck and bring your questions to Q&A and preferably put them in the forum, preferably by Friday. Okay, have a nice week and see you next